All right. So we have been discussing registers and counters. We discussed, data load, clear, and clock operations. We saw how we can transfer a set of binary bits from one register to the other and do it selectively. We can pick and choose between registers. We saw a little bit bigger picture. Instead of using regular wires to connect a flip-flop with another, we looked at a bus-based structure where you show multiple bits transferred from one register to the other. So obviously, it's a bigger picture. And then we finally saw a direct practical application of where you can use a combinational logic together with sequential logic for the first time ever. I don't know if you realize this is the first slide that brought together combinational logic and sequential logic in a real system. But when we went over the adder lecture, we only looked at adders. We didn't even consider the need to store an intermediate result. And for this slide, we noticed that you could always save the sum from every stage and add it back during the next cycle. So there is a concept of previous cycle, next cycle, which was not there in combinational logic because combinational logic doesn't have any history. Okay, that's how combinational logic and sequential logic work together. And we'll see more examples of it as we move forward. So hopefully this was a easy to relate to example. And I received many questions about this afterwards, which is very good. That means you have been thinking about it. If you haven't, please think about it and make sure that you understand the functionality. Okay. And if anything, even for your final exam, there could be an MCQ related to the foundational concept. I'll test you on your understanding. I'll not test you on your memory, because nowadays you don't really need to memorize anything. You have all sorts of resources to help you remember, but understanding is still necessary. All right. So shift registers. Okay. This is the new concept that we'll cover today. What it does is basically, you already know what a register is. It's a group of flip-flop, right? So a shift register takes a set of bits and it shifts them from either left to right or right to left. And depending on what you need, you could design different kinds of shifting. For example, you could design a shifter. Let me show you something. Like say you have 1101, a set of bits, and you're shifting it to the right. Okay. So what you can do is basically, let me change the color. So you take this one here, the other one here, 0 here, and this bit, which was at the edge, will fall off. It will be gone. Okay. And you can either fill the first one with 0 or 1 or whatever you want. So it depends on your algorithm, what you're trying to achieve. Or there could be another situation. You basically circle it back. So whatever it is lost from the edge will be the first bit. Okay. This is more like a cyclic shifting as opposed to, yes. Yes, it is lost. It is basically discarded. So I will show you both examples with this simple circuit, right? Notice if I zoom in, and I hope you can see this clearly. This is an optional feedback. Okay, I will talk about this feedback later, but for now, imagine that it's not there. So you have a set of flip-flop, and these are conventional D flip-flops, which will basically send the data to the output. Okay, and you are driving it with a set of just one input, and we are calling it serial in. Remember, get used to this terminology, serial and parallel. So when I say serial input, I will be providing one bit at a time in series, like 1 0 1 1 1 1 0 0 0, something like that. But in case of parallel input, if you have say 4 bits, you provide all 4 bits simultaneously, so they're processed simultaneously. We haven't really seen too many examples of parallelization here. To keep things simple, we have been just looking at serial input for now, but it is essentially not too difficult to do parallel. You just have to have multiple redundant systems to handle everything in parallel. Okay, so let's consider that you have a serial input and you'll be providing different bits, zeros and ones, through this. And just let's go through the chain. If you provide a 1, it will be eventually set as an output after the clock edge. And we can keep doing it. You can keep providing 1 0 0 1, whatever, and these bits will gradually trickle through the chain, right? They will ripple through the chain. And apparently, at every output node for every flip-flop, you'll have something, 1 or 0. And what happens is, as you keep providing more and more inputs, at every clock edge, this input goes to the output, this input goes to the output, and apparently they will keep shifting. Notice, isn't that physically happening? You're basically shifting the bit from leftmost flip-flop to the rightmost flip-flop. So if I take just one example here, imagine you start with 1 in this flip-flop as an input. During the first clock edge, let's just track the 1, okay? First clock edge, it will go to the next flip-flop as an input. Next clock edge, it will go to the other flip-flop as an input. Next clock edge to the other flip-flop. Final clock edge, it will go to the output. And the next clock edge, it will be discarded because there is nothing there. Okay? Does that make sense? So if you track just one bit, is it being shifted from left to right or not? You can see that? And I'm just tracking one input. But don't forget, there was another input sitting here. Imagine initially, say this output was 0. Initially, it was 0. So at every clock edge, the first clock edge, it will be shifted to this output. Next clock edge, it will be shifted to this output. And then here. Right? And don't forget, there was another input sitting in this. I'm just taking 1 as an example here. So first clock edge, it will be shifted to the next one. Second clock edge shifted to the next one. So notice, at every clock edge, you are basically shifting the content of every node to the right. So isn't that a shift operation? Okay. Let me use this waveform to help you understand what it means. Again, but you do see that it is a shift operation, right? At every clock edge. So this is synchronized. You give one clock edge, it shifts one stage, and everyone shifts one stage. Okay, so imagine that this is Q3, Q2, Q1, Q0, which are these 4 nodes. Can anybody tell me, to begin with, what are the bits stored in those 4 nodes? Just look at the waveform and tell me. At time equals 0, what are the bits, binary bits, stored in these 4 nodes that I've indicated? Please. What is Q3? Can anybody take a look at the waveform and tell me what is Q3 at time equals 0? 0. So this was 0. What is Q2? 1. What is Q1? 0. What is Q0? 1. Right? So we started with 0, 1, 0, 1. Is there a reason? No. It's a random choice. I mean, I'm just taking this as a random number. So now we will see whether or not this can be shifted to the right with every clock edge. Okay. Ready for it? As you know, the timing diagrams are tricky. If you lose track of one, none of this will make sense. All right. So let's do it. First of all, we will settle on an input. So we are assuming that we are providing 1 for a while. Remember, this is not just 1, 1. It is a set of ones. Basically, what if I keep giving 1 to a system? How will the waveform look like? Imagine it was 0 before, and then I gave it 1, and I keep giving it 1, 1, 1, 1, 1, 1. Is it just 1, 1? Sounds weird, but it is not just 1, 1. It is a set of ones. Does that make sense? How do you know how many ones I gave? Because you know the active time or time period of the input signal, right? You know that you are giving a 2 nanosecond pulse. So every 2 nanosecond you evaluate. So you know, if you have like 6 nanosecond and it is always 1, that means you have provided 3 ones in series. 1, 1, 1. Are you good? Okay, so without any loss of generality, let me just move it. Let's stay. So we decided to provide an input like this. So a set of 1 and then set of 0 and then 1 again. And remember, what is this? This is the very first input that you're providing. So when you provide 1, you just have to track whether this 1 is being rippled through the chain at every clock edge. Okay? Ready to pay attention? So we will track Q1 first. Let me just move this. It was 0, 1, 0, 1, right? 0, 1, 0, 1 to begin with. So let's see. Which color should it? Maybe green. Okay. So first, we provided 1 to the serial input. Okay, so let's track the clock edge. Where is my clock? This is my clock. And we are assuming that this is a rising edge triggered clock. I mean, a rising edge triggered flip-flop. You could always do falling edge, doesn't matter. Okay, so let's do rising edge triggered flip-flop. So for the first clock edge, this guy, this flip-flop will look at the input and see that the input is 1. So what will it do? It will try to send this input to the output and see. Did it do that? You see that it basically sends the input to the output, and track the arrow. This arrow shows this input at SI, serial input, was sent to the output. That's why you suddenly have 1 here. Are you good? And please notice there is a subtle indication of a delay. See, this is the clock edge, but we never just change it at the exact clock edge. We change it afterwards. That is the reason why you have to keep track of things. Are you all good? Okay. By the way, everything has a symbolism. There is a reason why, by the way, you're looking at this data and you show that this data is available here. You don't show that the data is available right here at this point. Can anybody tell me why? Because the data is only valid after a hold time. Remember, there is a setup time and there is a hold time. If you have the data here and then change the data right away, it will be invalid. So you have to you indicate that my data that was provided here is now available as a valid data at this point after the hold time. Make sense? Okay. All right. So we have successfully managed to send this input 1 to the next level. And by the way, we should keep, let me just use a common color. So let's keep track of this green dot. All right, let's keep track of this. For the next cycle, let's see what happens to this green dot. For the next cycle, which is this one. All right, are you ready for it? This green dot will be held at Q3 because Q3 got this green dot, which is 1, and it will hold on to it because that's what flip-flops do. They hold on to the data until the next clock edge arises. When the next clock edge arises, it will take the input again and change its output or discard its output or do something. So this green dot at the next clock edge, remember, this is the green dot. I hope you're not getting confused with the green dot, right? This is the data essentially. At the next clock edge, this will be sent to the next output, which is Q2. Okay, so notice at the next clock edge, which is here, this dot is sent to the next output. You see the arrow? Follow the arrow. And what happens to after this clock edge? You wait for the next clock edge. Until then, this flip-flop holds on to the data. And then at the next clock edge, it sends it to the next flip-flop. And then that flip-flop holds on to it until the next clock edge. And at that time, it will send it to the final output. Do you see that? You see what the flip-flops are doing? They're not just handing over the data. They're handing over and holding. This staircase-like situation, this shows the memory effect of flip-flop. It can hold on to the data. If you stop the clock, it will hold on to it forever. Right? If I decide to abruptly turn off the clock, disable the clock, that means the data will be stuck. But do you see that this data is being handed over from Q3 to Q2 to Q1 to Q0? It is being shifted from left to right. You see that? Okay. If I tracked, instead of tracking the very first input, if I start tracking from this point and try to see what happens to that, you will see exactly a similar staircase-like structure. So every bit of data is being shifted to the right. Are you all on the same page? Okay. One other minor point. What happens to the last output? So when this final flip-flop gets the input, say 1, and maybe it was 0 before, it just sends this to the output and it becomes 1. And that 0 that it had before will be lost. So it is like discarded. It's no longer there. However, if you create a feedback loop like this, connect the output to the input. Connect the output to the input. That means you don't even have to provide any serial input at all. No input necessary. The output will serve the next input. You see my point? So this 0 will go back as the next input. So this is more, yes.
That staircase you showed a right shift.
Yes, it is a right shift.
So will the left shift be upward from the bottom?
Yes, yes. But by the way, that's a good question, just for me to clarify. Don't get confused as to the numbers, basically. So we are looking at D3, D2, D1, and D0, the way we have arranged this. But imagine if you start providing the input from the other side and just flip it over, it could be the left shift. So basically, there is no fundamental difference between left shift or right shift. Like you're shifting serially, that's all. Okay? But when it comes to cycling shifting, and the easy signature would be, say, 1101, you shift it like this. So it will be 1, 1, 1, 0. You see my point here? Like a cyclic shift. Easy fix would be to just connect the output to the first input. And there you go. You keep cycling it. Have you seen one of those like Christmas lights that people put on their houses and they like cycle through different, flickering sequences? It always cycles through. Essentially, what they have is a shift register. Right? It shifts from, it's like, shifting from one state to the other, and it goes back, always goes back. So that's how, like, these primitive circuits are used in primitive things, like small, low-tech stuff. But it can also be used in high-tech stuff, by the way. But they're going to be very tiny part of the high-tech stuff. All right. Are we all good so far? And trust me, you will only fully understand when you go back and think about it yourself, try to make sense of it, try to track it yourself using pen and pencil or whatever. Don't rely on just, listening to the class. Because at some point, you'll forget what I said. All right. So, all right, let's move to the next one. I'm moving, for the interest of time, I'm moving on. I'm assuming that you got it. But if you didn't, you know what to do. Reach out to me. All right. Now, we will discuss a new concept called counter. This is a very important circuit for digital electronics. In fact, electronics in general, okay? It's kind of like a, as the name suggests, it counts. Basically, it goes from one level to the other and it resets. In digital electronic sense, we represent it in a little bit difficult way. A circuit that cycles through a fixed sequence of states is called a counter. It sounds like a really fancy thing, but imagine, I'm going to tell you, give you a very simple example. Imagine you are counting down to 0 to 9, say, and then back. So 0, 1, 2, 3, blah, 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 9, and then you are going back. So how many states do you have? You have 10 states. 0 is a state, 1 is a state, 2 is a state, and so on. You have 10 states. And then you are resetting it. So basically, if you design a circuit that counts from 0 to 9 and then resets back to 0 and then repeats the process, that will be the counter. And the way, and not every counter needs to be like this. Some counter could count from 0 to 3 and then reset. That is a different counter. So you define the states that the counter will cycle through, right? It is a system that keeps repeating itself. Does that make sense? And we'll see how this counter could be implemented in a simple circuit using just flip-flop. And notice, we are deliberately using flip-flops to implement these circuits to show the power of sequential logic. Okay, this is the circuit that counts binary digits. Okay, 3 bits binary, and I'll show you how to do it. Before we see how this circuit came into being, it doesn't fall from the sky. We have to design it logically. Let me show you how to do it. First, let's see how the numbers are counted with 3 bits. Okay, we have seen this many times, this truth table many times, didn't we? All possible combinations with 3 binary digits. So you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and blah, blah, blah. And it ends in 111. That's the final count. And after that, you can reset back to 0, 0, 0. So how many numbers are you counting here? How many states? 8. You're counting 8 states. So this is another example. Instead of having 10 states, you can have lower than that. You have 8 states here. Okay. We will do some observation here. Notice. And deliberately, we are going to use T flip-flop to design this circuit. That doesn't mean you only need T flip-flop to design counters, okay? Don't get it this way. But did I tell you that people figured out an interesting feature in JK flip-flop, the toggle feature, and then they made a dedicated flip-flop out of it, which is known as the T flip-flop, whose only purpose is to toggle or not toggle. How many of you remember what the T flip-flop does? It has a T input. If the T is set to 0, the output doesn't change. It will remain whatever it was. If it was 0, it will be 0. If it were 1, it will remain 1. But when you set toggle equals 1, at every clock edge, it will change itself. 0 to 1, 1 to 0, whatever it was, it will change itself to the other one. Okay? I hope you remember that. All right. Super simple flip-flop. Actually, one of the simplest flip-flops. That's why we're using it to design the circuit. Because you don't have to worry about all these other set and reset, whatever. You don't want to manually do anything. You just want it to keep cycling itself. So a T flip-flop. Okay, notice. I bet we have never thought about it this way, thought about this truth table and counting numbers this way. Let me show you. So when you go from 0 to 1 and 1 to 2 and 2 to 3 and blah, 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 and so on, gradually, look at the first beat, very first beat. Have you ever seen that at every count, the first beat always toggles? You see that? The first beat will always toggle between counts. 0 to 1, 1 to 0. It will never stay the same. Okay? How can I design so if I try to represent the first bit with a flip-flop, so since you have 3 bits, one flip-flop deals with 1 bit. So how many flip-flops do you need? 3, because you're dealing with 3 bits. Okay? So for the first bit, the flip-flop that will represent the first bit, it will always toggle. How can you design a T flip-flop that always toggles? Just take a flip-flop, set the input to be 1. That's it. Its output will always keep toggling between every clock edges. Does that make sense, folks? So I'm taking care of the first bit here. All right. Oh, by the way, before we get to this, you have 3 flip-flops. 1, 2, 3. And they're all driven by the same clock. So let's get it out of the way, all right? Clock is basically shared amongst all the flip-flops. That's why they're synchronized. So they update themselves with the clock. Okay, the only thing that we have control over, we don't have control over the clock here. It will just keep coming. We have control over the input. We can control the input to make them switch the way we want to. So the first bit, we are making it switch every time. So it is always switching. We deliberately force a 1. So let's see the second column here for a second, all right? Let's see the second column. Have you noticed something? So between the first 2, it didn't change. So it didn't toggle. And it toggled here. It toggled from 0 to 1. Notice when it toggles, your first bit was on, or 1. Okay? And again, when did it toggle again? Here. When it toggled, your first bit was always 1. And again, it toggled here. And notice your first bit was always 1. Basically, you can logically think that when you add 1 to the first bit, you have a carry, and that's where the second one changes, right? Does that make sense? So do you see that the second one only toggles? Sorry. The second bit only toggles when the first bit appears to be 1. Otherwise, it doesn't change. See, here you don't have any toggling effect because your first bit was 0. Here you don't have any toggling effect because your first bit was 0. Does that make sense? So can I say that B or the second bit will toggle when A is 1? Can I say that? Are you still with me? If and only if A is 1, that's when we should toggle. Otherwise, we shouldn't. So see, this simple concept could be represented like this. Take the output of A, basically the first flip-flop, and connect it as the toggle input. So when A is 1, it will toggle. When A is 0, it will not toggle. Make sense? Okay. And we are doing it logically, by the way, without any strategic method. I'm not giving you a K-map or anything like that to design this circuit. We're just observing and trying to come up with a circuit that achieves so. Okay. All right. So we took care of the first 2 bits. How about the third bit? Let's go back to the table and observe again. And trust me, most of these discoveries start from observation. People see a pattern. There are some people who are really good at recognizing pattern, right? And they discover something and they backtrack. We don't invent K-map out of the blue, right? After many years of manual work, people realize, hey, there is a bigger story here. There is a strategic approach that we can take to generalize this for everybody so that people don't have to keep looking at patterns. And we are getting there. Okay, so let's see the pattern for the third one. For the third one. Hey, there is. Do you see any toggling effect here? No. Any toggling effect here? No. There was just one case where there was a toggle, which is this one. And we happen to notice this occurs when A and B are both 1. For all the other cases, at least one of them is 0. Does that make sense? Oh, by the way, there is another toggle. After this state, you go back to 0. Don't you go back to 0 after this? But notice, even then you have both of them as 1. Okay? So can I say when A and B are both 1, only then we should toggle. And if one of them is 0, we shouldn't toggle. What is the function, Boolean function, that is 1 only when both inputs are 1? AND gate, right? If you remember AND gate, right? As long as one of the inputs is 0, it will always be 0, except for the fact that when both inputs are 1. So I will rely on A and B. I will see whether both of these are 1 or not. So that's what you see here. Take B and take A, take an AND gate, and the output of the AND gate should drive the toggle signal for the third flip-flop. When both of these are 1, the third flip-flop will toggle. If not, it will not toggle. Does that make sense to you logically, folks? So if you keep monitoring, like if you take an oscilloscope, for example, or any other, say, digital logic examiner, okay, analyzer, and if you follow along A, B, and C output, you will see them changing from, at some point, you'll see 0, 0, 0. Next, 0, 1, 0. You see my point here, right? Sorry, 0, 0, 1, and 0, 1, 0, and 0, 1, 1, and so on. So it will keep changing as the truth table, from 0, 0, 0 to 1, 1, and back to 0, 0, 0. So this is a counter, which counts from 0 to 8. Okay, if I want to count higher, add another flip-flop and figure out the logic for that toggle signal. Does that make sense, folks? Okay, I could give you a homework. I'm not gonna do that. I know, like, you guys must be very stressed out towards the end of the semester. I'm not gonna give you any random homework, except for the ones that are definitely necessary. But imagine there could be a homework to ask you to put in a 4th toggle signal. So what you do, I'm just telling you what to do. You just go back and make a truth table with 4 signals and see for the third pattern, sorry, the 4th pattern for the 4th bit. And if you find a pattern, great, you design the circuit accordingly. But you see, this is a tedious process, and not everything will have a really nice pattern like this that human being can perceive. Oh, there you go. I know the pattern, that's why I'm telling you. But if I didn't know it, it will be impossible for me to discover the pattern within my class period, right? So there has to be a better way. What is the better way? And the last slide will show you the actual systematic way to do so. This is the last slide for this lecture, all right? Ready to do it? This is basically our well-known K-map. We could use our K-map to design these flip-flop circuits as well. Okay, let me show you how. Let's start with, it's a different type of table that we use for sequential logic. Because in sequential logic, you have to have a concept of previous and next. Previous and next. In combinational logic, it's always now. There is no previous, there is no next. It's right now. Okay. So imagine this is, so we are differentiating between our present state for the flip-flops and next state. So this is A, which is the present state. A plus is the next state, and so on. So you have 3 flip-flops. They all have their present state and next state. Present state and next state. Are you good so far? Okay, so imagine, behave like a counter. This is our first state to begin with. Everything is 0, 0, 0. All right. So for the first bit, what will be the next state, folks, to count? What will be the next state? 1. If you begin with 0, next state should be 1. You know this. How about the second flip-flop? For the next count, it should remain 0. For the next count, so basically what you do is you take the next number and populate it as the next state, don't you think? Notice, for the second state, the third number will be the next state. Do you guys see the pattern? Is it difficult? Is it difficult? So you understand that for this particular state, the next state will be its next count. How about the last one, triple one? For triple one, what is the next state for triple one? 0, 0, 0. That's why you write 0, 0, 0 here. Okay, so you populate this table. There you go. You have populated the present state and next state already. All right, done. You cover 2/3 of the table. The last third, last 1/3 is here. So we have to decide what is your final decision here. Your final decision is, what do you do with the toggle signals? Toggle A, toggle B, toggle C. What do you do with the toggle signal? How do you change the toggle signals to achieve this state combination, present state, next state combination? Okay. So as I told you here, for toggle A, since you always change things, okay? So notice, I will be using a different color here. So you have to pay attention because it will get super messy. Are you ready? I'll begin drawing now, all right? So at this stage, I'm gonna make a decision whether or not I will toggle. Should I toggle, folks? 1 to 0. Should I toggle? Yes. If yes, put a 1. If no, put a 0. Okay. Here, between these two, should I toggle? Yes. Should I toggle? Yes. Should I toggle? Yes. And you get the point, right? At every point, you just see whether you need to toggle and update the corresponding toggle signal accordingly. It is always 1, of course, as you imagine. So it's not really showing you much. Let's go to the other one, and it will make more sense. Okay, so between these two, 0 and 1, should I toggle here, folks? Okay, set. Let me show you. So between these two and this two and this two, okay, at every stage, sorry, I think I showed you something wrong. Our A and A plus are here. Sorry. Let me rephrase that again. All right. Let me rephrase it. So this is my B plus. This is my B. Let's take back what I just told you. Look at these two numbers. I was marking the wrong numbers actually, right? Should I toggle here, folks? Because that didn't change. So 0. Between these two, should I toggle? Yes. Between these two, should I toggle? Folks, is it changing? No. So I shouldn't toggle. So toggle is 0. So you decide accordingly. All right. Okay, let me go back and explain the first one because I kind of mismarked that. So compare between A and A plus. Okay. So 0 and 1. Should I toggle? 1 and 0. Yes. And you can keep saying yes. So that was it. All right. Let's see the final one. Let's see the final one. Starting with this one. Our present state to next state. Should I toggle? No. When should I toggle? Let me just get to that one. Here, 0 to 1. Yes, and then that's why you have a 1 here. And the other toggle case would be this one, and you put a yes there. So you essentially create a truth table, don't you think? Isn't that a truth table? Okay. Now, it's just the case that to get to the final output, you need 2 set of input. Just take a look at the truth table and try to appreciate the difference between the sequential approach and combinational approach. For combinational logic, you just needed A, B, C, and these were your output. Done. There was no next state or previous state. There was just state. But here, you need these 2 situations just to get an understanding of the final output. You cannot get to the final output without this. Okay, remember. Let's take a step back and see which inputs are you controlling, folks? You as a user externally, which one are you controlling? Are you controlling A plus or A? A. You are not controlling any of these plus inputs. You're controlling this ones. And what is your final output? These are your final decisions, essentially. So you now go back, remove this next state from the picture, and treat it like a truth table that you have seen so far when you worked on K-map. Can you make a K-map with this truth table, folks? How many output signals do you have here? How many? How many output signals do you have? And by the way, there is no, this, first of all, I know you might be getting confused. These are marked as input, but for the time being, just ignore them. Okay, just don't look at this wording, flip-flop input. Just forget it. I'm telling you, these are outputs. These are outputs for what? These are outputs for combinational logic. K-map is used to design combinational logic, not flip-flop. We are designing combinational logic here, all right? So for the time being, imagine this TA, TB, TC are output of a combinational logic that you are going to design. Still with me? Still with me? All right. I'll show you how that thing comes into being. Okay. So forget about this now. You have 3 inputs and you have 3 outputs. When you have 3 outputs, did we see multi-output K-map, folks? How many K-maps do you need? No. For 3 output, you need 3 K-maps. Remember, like when you had 2 outputs, Y1 and Y2, what did you do for sum and carry for an adder? You had a separate K-map for sum, you had a separate K-map for carry, didn't you? Remember that now? Okay, so since you have 3 outputs, TA, TB, TC, you'll have 3 K-maps. First, for TC, the other one for TB. I haven't drawn it for TA because I will. Ready for it? But I will start with TB and TC. For TC, can you help me populate the K-map based on this combination? Can you guys populate it? Are you confident that you can populate it? Take AB and C like this and then populate TC. And once you get it, can anybody help me get TC from here? What is not changing? AB. So TC equals AB. Can I write it? Write it? All right. How about this one? If you put in all the ones corresponding to TB, you get these 4 ones. What's going to be this expression, folks? Does C change? Yes, so we don't take C. Does B change? Yes, we don't take B. What doesn't change? A, and it is 1. So TB equals A. Are you good so far? Now, we have a unique situation for the other one. If you draw BA and C, this is the first time ever. Nobody asked me this question. It's a fun MCQ, honestly. I could have given it to you during the quiz. But what if everything is 1? What if everything is 1? It is a function where everything is 1. What changes here? Like basically, you have to take everything. Remember, we only take the things that don't change. Is C changing from between these two? Yes. Is B changing? Yes. Is A changing? If you have 4 rows, everything will change. Don't you think? You don't get what I say. So, okay, let me change it back again. Imagine if you go from here to here, will B change? Yes. Will A change? Yes. Will C change? Yes. So if you take everything, then everything will change. So what do you take to get the function? You take nothing. So what happens is you take just function equals 1 because the function is always 1. The function is always 1. That's why function equals 1. Make sense? So if I draw the K-map for TA, your TA will always be 1 and TB was A and TC was AB. Do you see that now? Just from the K-map? Are you good? Okay, now go back. And I told you TA, TB, TC are output of the combinational logic. Okay, let's go back. Is this a combinational logic circuit, folks? This is TC, which is AB. Oh, let me make it better. So this is our output TC, which is AB. Aren't you getting AB here? Okay. How about this? This is TB, which is basically A. And this is TA, which is just 1. So these are outputs of your combinational logic that you provide to the flip-flops as inputs. So your combinational logic output is basically the input for the flip-flop. Okay, does that make sense? That's why it was marked as flip-flop inputs. But you don't use K-map to get the inputs. You use K-map to get the output of the combinational logic. And then there's, yes. Not necessarily. Not necessarily. This is an interesting thing. You can give it a shot, right? It's not like, it will keep repeating itself. It may not be. So I don't want to comment on that without seeing the pattern. It's a good question. So his question is, if I add an extra bit, right? Will it just keep repeating this process? We don't know. We'll figure out. We can just make a truth table and see how the K-map looks like. It might be as simple as that, or it may not be, right? I don't remember this on top of my head. All right. Does that make sense, folks? But can you do it? I highly recommend it. Challenge yourself. Yeah, just make a bigger truth table and see whether that's really the case. If so, there you go. That's interesting. Are you good so far? Okay, so that concludes this lecture, and we have a few minutes left, 5 minutes. So I will at least get started on the next one so that we have some momentum, and of course we'll finish it in the next class. This is supposed to be a tiny lecture because we highlight a very specific concept, and the next lecture will take it to the depth. We will look at analysis of clock sequential circuits, which we are already doing. And I decided to use an example, not just it's from the textbook, of course, that illustrates the utility of sequential logic furthermore, and also illustrates the design process. Okay? So this is a parity checker. What is a parity? What does parity mean, right? So it's basically, imagine if in a binary stream of numbers, you have zeros and ones only. And if you keep count of 1, if you have an odd number of 1, it is called odd parity. If you have an even number of 1, it's called even parity. Okay. How is that useful? Here is how. Notice. Okay. So imagine you have 7 bits of data, and you have an extra bit that indicates whether it is even or odd. Are you still with me? And this is particularly useful when you transmit information, when you send some information from one place to the other, and you have to receive. Because during transmission and receiving, there is always a higher chance or probability of bit flipping or signal transmission error. Okay? That's when you have to check whether what you received is correct, is the one that was transmitted. So imagine before you send this 7-bit data, you always, you made it, this is a design decision. This is a design decision that you take. You always make it odd parity somehow. Are you hearing me? If you don't hear me, you have to read through chunks of text like this from textbook, and then it's not going to be fun, honestly. So 7 bits, you have 7 bits, but you as an engineer decided whatever I send, I will always make it odd parity. You have decided it. Okay. So is this odd number of ones? How many ones do you have? 0. 0 is an even number. So how can I make it odd? I add an extra 1. This is my parity bit. I add an extra 1 to make it odd parity. Okay. Let's look at the next one. How many ones is there? 1. Is it even or odd? It is already odd. Do I need to add a 1 to make it odd now? If I add a 1, it will be even now. So it will be counterproductive. So I will send a 0 instead to keep the parity odd. And again, how many ones are here? 1, 2, 3, 4. It is an even number of ones. But I decided to make it odd all the time. So I will add an extra 1 to make it odd now. You see my point here, folks? Okay? If you decide to make it even, you just do the opposite. Doesn't matter. So somebody decided to make everything odd when they send. So this is an odd parity example. So you send 8 bit of information, but the last bit, it is essentially used to create the parity. and the other 7 bits are useful information. Are you all with me so far? What is the benefit of this approach? Let me explain that. We have 2 minutes, which is good enough to explain the benefit. So imagine you send this information. You know, all of your information are sent in odd parity. If somehow one of the bits flips from 0 to 1 or 1 to 0, will it be odd parity anymore? You decided that everything I send will be odd parity. Just one bit flips during transmission. You don't know which one, but it's no longer going to be odd parity. Do you see my point here, folks? The moment anything flips. So that's how you detect error. Of course, you cannot pinpoint which bit flipped. Did this one flip or the other one flip? What you do is you ignore that entire chunk. 7 bit is not much, honestly, but you see my point here. So you always have a set of bits and you have a parity checker. If you do it more often, then you'll be wasting a lot of bits because these are essentially useless, except for the checking, right? But if you imagine, I decided to have like 20 bits and I'll check the parity for 20 bits with 1 extra bit. Then you are uncertain about the position of the parity, like of the error. You have to clear all 20 bits if there is an error. So that's a challenge, right? Keep in mind, you have to discard a whole chunk of data. But if you decide to do every 4 bit, I'll have a parity. Every 4 bit, I have a parity. So every time you encounter a mismatch in parity, you have to clear those 4 bits, which is good. You don't have to discard a lot of data. But it is bad because you're wasting a lot of parity bit. If you have 10 bits, 2 of them will be parity. So you have useful 8 bits. You see my point here, right? It is a design choice. How often do you insert parity bits, or how less frequently do you insert parity bit? It is a design optimization, but we do use parity bit. It is used everywhere. So it is ubiquitous. Super simple concept, but it is used everywhere. We will learn in the next lecture, next slide, how to design a parity checker with just a single flip-flop. That's how powerful flip-flops can be. All right? Okay, thank you.